Hello, everyone. I'm very happy to see that it's so full again. I think we will have to start with pre-registration soon. But welcome on this Friday to our third edition of Nachts auf der Sternwarte of this semester. Our presenter today is Alice Zocchi. She's a postdoc here at the Institute, and she will tell us about the object she studies with all her heart, which are the globular clusters. And well, for all of you that have already been here, you have a small survey in front of you. It would be great if you can fill it up. And today, again, we have 3 posters to give away. So if you want to participate on the raffle for one of these posters, you can write either your name on the survey or your seat number or something that can identify you. And at the end of the talk, we will just pick 3. And also after the talk, for those of you who want to visit the Great Refractor, Meinrad is going to help us with that. Oliver cannot be here with us today, but yeah, he sent Meinrad he was very kind to come today to help us with that. And well, Alice, the floor is yours.
Thank you. Can you hear me? I hope so. Good evening, everybody, and welcome, and thank you for coming. Yes, so today I'm going to talk about my favorite objects in the world, in the universe. So star clusters, and in particular globular clusters, which are a specific type of star clusters, of which I will tell you more later on. Before diving in, let's take a step back. Let's take several steps back. So let's start from where we are now. So yeah, we are in Vienna. And I want to tell you a little bit more about where I was before and what happened before in my life. So before coming to Vienna, I was in the Netherlands. I was a fellow at the European Space Agency, and I stayed there for 3 years. Before that, I was for 1 year in Bologna as a researcher. And before that, I was in the UK, in Guildford, at the University of Surrey, on another fellowship for another couple of years. And before that, I was in Milano, and I was doing my PhD and my bachelor and master thesis over there. So as you see, I moved around quite a bit, which is not unusual for astronomers. And yeah, so I studied in Milan, but I'm actually not from Milan. I grew up in a small town. And when I was a kid, I was always super curious. I was asking 10,000 questions all the time. My parents loved me, as you can imagine. And I wanted to know. I wanted to know everything. I wanted to know why things happened, how things happened, and I wanted to know things that happened before I was born. So I kept asking my grandmas how were mom and dad when they were kids, because I didn't know that I didn't met them back then. Or how did they meet? How did they live together? How they ended up together? And of course, I asked my grandmas because they were there. They could witness this and they could tell me about it. I couldn't because I was not born yet. But then when I grew up and I started, asking questions again, I kept asking the same kind of questions, but not about my parents anymore. Now I ask these type of questions about galaxies and about the universe. I still want to know what happened before. So how was the universe when it was young? How were galaxies when they were young? How did galaxy form? What type of processes brought to their formation, to their evolution? How did they ended up being how they are today? Unfortunately, my grandmas were not around back then, so I couldn't ask them. I need to find someone else that is as reliable as my grandmas were in telling me the stories about my parents' life. And there is actually somebody who is like the grandparents of the universe, if you wish. And you guess it, it's globular clusters. So first of all, what is a globular cluster? A globular cluster is a collection of stars. You can imagine them a little bit as a swarm of bees, but made of stars. They are mostly made of stars, so they basically contain no gas, and we think that they contain also no dark matter, which makes them easier to study because it's just stars. In the center, as you can see, they are very bright, and that's because they are among the densest places in the universe. And over there, the density is so high that is basically 10,000 times as high as in our solar system, in our solar neighborhood, sorry. So to try and understand a little bit what that means and how that is, just imagine that all the stars that you see in the sky would come 100 times closer to us. That would mean that they will become much, much, much brighter. And that would mean that if we were in such a system, we could go outside at night and read a book by the light of the night sky, which is a pretty nice picture. But stars are moving, so it's also very confusing if you think about it. So yes, these objects are very interesting because they are among the oldest objects in the universe. We think that they are the first coherent structures to form in the universe at a subgalactic scale. And we know that because we have seen them very far, far, far away. So this is an image of a protoglobular cluster that has been observed thanks to gravitational lensing and with the Hubble Space Telescope. This is at a redshift of 6, which means that this image is so far away that the light took 9.5 billion years to come to us. So this means that this protoglobular cluster, this young little thingy, at this point has more than 10 billion years. This is very interesting because then, by looking at these things very far away in the universe, we can try and start to understand how they formed and how they were at the very beginning. And thanks to JWST, which is this telescope over here that was launched last Christmas, very nice Christmas present for all astronomers in the world. So we now can take better pictures of these things. So this is just to show you an example of how things improved from HST to JWST. So this is the same type of system, and the little dots that you see here are just images of a lensed globular cluster. So this is the thing that people are looking at to try and characterize the protoglobular clusters back then, far, far, far away at the beginning of the universe. So yes, globular clusters are old, so that's good. We know that they were there when galaxies formed, they can tell us about it. But were they actually in galaxies? Well, yes, and actually globular clusters can be found basically in all the galaxies. So over here you see M87, it's a giant elliptical galaxy. You see that it's elliptical in shape, so spheroidal, but a little bit flattened. And this is a galaxy, so is 1 million times larger than a globular cluster. And indeed, it contains more or less 15,000 globular clusters. And some of the dots that you see in this image are actually globular clusters that you can see even at this distance. So this galaxy is several megaparsecs away, but still we can see the globular clusters. And we can see them because basically, globular clusters are made of 1 million stars, more or less, and they are all together, closely packed, so their light is really bright, and seen as a coherent systems, we can see them from far away, and they are still bright enough to be visible and to be detectable. So this is great. And so galaxies like this are a goldmine for globular clusters, even though at these distances we can only see them as dots. Other galaxies have a little bit less globular clusters, depending on how big they are. So this is a galaxy in the Fornax cluster, so it's a little bit closer, and you can see that the clusters look a little bit extended, so they are not point sources anymore, they're not dots. You can see that there's something going on there, that there are some more stars making them up. But this galaxy is very small, and it only has 4 globular clusters, so this one's marked with the circles. So yes, over here, there's not so much information maybe, but still a lot can be done, especially because the individual stars in some cases can be resolved. Another example is the Andromeda galaxy. Andromeda is a spiral galaxy, is in the neighborhood of the Milky Way, so it's very close to us. And this is a piece of Andromeda that has been observed with very high resolution and for a very, very long time to get very, very deep and very accurate images. And in this figure over here, like on the board at the moment, there are 2,500 globular clusters. So some of the dots that you see are globular clusters. So this galaxy also has a lot of clusters that could be studied. And in some cases, they can even be partially resolved. for example, if we make this a square over here a little bit bigger, you see that there are some overdensities of stars, these ones marked like this, that correspond to these images on the right, and they are globular clusters that have been imaged a little bit more in detail, so you can see a little bit the stars that belong to them, so how many stars are there and how they are distributed. Of course, it's not the most accurate image ever, and you can only see the very, very bright stars at that point because Andromeda is kind of far away with respect to our own Milky Way. So it's not the greatest, amount of information that we can get, but still it's useful. Yes? Yes, yes, yes. Okay, so I repeat the question. So the question is about the colors of the stars. So the red and the blue stars are stars that have maybe a different composition. It could be that some of them belong to the cluster, some of them are behind, or it could be that they all belong to the cluster or to the galaxy and have just they are just in different stages of their life, or they have a different composition to begin with. So it's all stars that belong to the galaxy, and at these distances, there's only that. So it can only be stars over there. But yes, yes. Okay. So I think that well, I mean, you have a lot of other information. So you have like the light that you see can tell you a lot already, and can position that star in a certain position of the color magnitude diagram. So it can tell you like how likely it is that this star is a star, or it's something completely off. And if it's something completely off, it can be redshifted. It can be something that is redshifted, but not a star. Because redshifted stars, it means that they are far, far, far away. It's not very easy to see that. So it's normally when you see something redshifted, it's galaxies, because then they are a little bit bigger, a little bit brighter, and then you can see them better. Because otherwise the light gets kind of lost along the way. Is this answering? Good. Okay. So yes, globular clusters in all the galaxies. And we can see them with the different levels of detail depending on where they are. What about the Milky Way? Are there globular clusters in the Milky Way? What do you think? Yes? How many? How many is a few? 10? Who says more? I have a 10. Thousands. Oh, a little bit less than thousands. Okay. About 150. So the Milky Way is not that big. It's a little bit more than 10, but not 1,000. So halfway through. So yes, this is an image of the Milky Way that has been taken thanks to the satellite galaxy, the satellite Gaia. So this is not a picture of the Milky Way, but it's just a collection of dots. So this has been created by individual images of the stars that Gaia took. And over here you see the plane of the galaxy and basically the entire sky put up in this image. And in this image you can see a lot of globular clusters. And I want to show you in particular two of them that are very important. So let's enlarge this part of the plot. Let's do some other polls. What is this? I heard it. Yes, the Large Magellanic Cloud, indeed. And what about this one? The Small Magellanic Cloud. Good. What is the dark spots over here? What are the dark spots? Dust. Good. And over here, what's over here? The bulge, yes, the center of the galaxy. So over here we have the nuclear star cluster that is at the center of the Milky Way. Okay, but where are the globular clusters? Well, for example, these two, they are the most massive globular clusters in the galaxy, and they have been widely studied, so there are a lot of observations that we have about this. So this one in the top is Omega Centauri, and this one in the bottom is 47 Tucanae, and 47 Tucanae is very close to the Small Magellanic Cloud, and that has been useful for some of the observations that have been done on its stars. Okay, so this is, the second part of why globular clusters are useful, because they are in all the galaxies. And so if we study globular clusters, we can get information about the galaxies that they live in, and about the young universe, because they are so old. The problem is that many of my colleagues see globular clusters like this, like a dot. Why? Because they work mostly on galaxies that are not the Milky Way and that are far, far away. So of course, at that point, you cannot really resolve that much the globular clusters. So for many astronomers, globular clusters are useful, bright dots that happen to be on the top of their galactic images, and that can be useful to do some nice things. To me, they are a little bit different, because what I look at are globular clusters within the Milky Way, which are very close, so we can really distinguish their stars. So to me, a globular cluster is a collection of stars distributed in a certain way, with the high density in the center, as we were saying before, and density that goes a little bit down in the outer parts. So outside, in the outer parts, the stars are more spread out. They are not so close together to each other. Then these stars have colors, and they have different brightness. So you can have stars that are more red, stars that are more blue, stars that are brighter, stars that are fainter, and they are all mixed up together. And then, most importantly, my favorite things, stars move. So you can connect, you can attach a velocity or a proper motion, so a velocity along the line of sight or a proper motion on the sky to each of the stars in a globular cluster. And that can help us a lot in understanding what is going on. So this is my favorite part of all the information that we can get on a globular cluster, because it tells us a lot about what is going on inside. Why is that? Because, as I said before, stars move. They constantly move. And in a system like a globular cluster that is made of stars, stars cannot go wherever they like. They have to follow some rules. It's like, these stars are dancing around like in a ballet, but when you go and see the ballet, you don't see the dancers do whatever they like, because otherwise the choreographer would, get angry. And in this case, stars also have a choreographer that decides which movements are allowed and which movements are forbidden. And the choreographer, in this case, is gravity. And the stars in a globular cluster move according to the gravitational potential that is generated by all the other stars and themselves as well. So they are systems that are called self-gravitating, because it means that the stars orbit in the potential that they contribute in creating. So they are held together by their own gravity. So in this simulation, you see that some stars are doing some fancy stuff. They are becoming brighter or yellower, and at some point they disappear. And this is because in this numerical simulation, not only the stars are moving, but they are also evolving. Because in time, stars change. So they evolve, they change their appearance. And at some point, they become neutron stars or white dwarfs or black holes, and we don't see them anymore. And that's why they disappear. But the important thing is that everything moves in the universe, but in particular in globular clusters. And by the movement of the stars, we can say a lot about what is going on inside and about what is happening in these systems. Okay. The problem is that for a very, very, very long time, globular clusters have been considered simple stellar systems. And whenever you hear a scientist saying that something is simple, it means boring. It means that we know everything about it, and there is no point in studying them. So for a very long time, globular clusters have been seen as systems that have a simple geometry, so they have been approximated as spheres, Spherical geometry, the easiest thing. You all know the jokes about the spherical cows that physicists like. So that's the idea. So a sphere, the easiest thing that you can think of to describe. They have also been considered to have simple dynamics. And that means that if you take a star and you see its velocity and you see the velocity of all the other stars, they end up on orbits that are more or less all of the same. So they more or less all similar to each other. And so there's nothing to learn by looking in detail in what they are doing. And another thing is that they have been considered to be simple stellar populations. What does it mean? It means that they were believed to be formed by a single molecular cloud, so with stars that are born with the same composition, with the same properties, and that in time evolve to occupy a line like this, which is called an isochron, on a plot that is very widely used by astronomers, which is the color magnitude plot. So on this axis, you have the color, and that's why you have stars with different colors, but because they end up in different parts of this plot. And also the brightness. So the brighter stars are up here, and the fainter ones that we probably cannot see, mostly cannot see, are down here. And this is the shape that a coherent stellar population assumes in this plot when it arrives at a certain age. And it's due to the fact that stars with different mass evolve in a different time. So the stars that are the largest burn the fastest. And so they evolve away from this line over here, which is called the main sequence. So they end up going the other way. So the idea is that if you take a globular cluster, and this has been the idea for a very long time, you look at all the stars, you measure their color and their brightness, you put them all together, and you find a line in this plot. And for a very long time, a good astronomer, a good photometric astronomer, was the astronomer that could get the cleanest sequence in this type of plot, because it would mean that the data were exquisite, because all the lines, all the stars align as the theoretical models predict. But then, as I said, simple is boring. It means that globular clusters are easy. They look like a pandistelle, which is an Italian cookie, and it's the easiest thing that you can think of to explain how a globular cluster is. A collection of stars, round, they don't move in a fancy way, they don't move at all, these ones, and they are all made of sugar in this case. But then, is this really true? Is there really nothing else to learn? Well, I guess the fact that this talk is about globular clusters is kind of a spoiler on the type of answer that this question has. But let's think about why this was the case. So, okay, they were considered simple, and they were considered simple because this is the image that we had of them. This is an analogy, of course. But, so if you see something like this, yeah, okay. It's a collection of squares, different colors, yeah, all more or less of the same size. You can describe them all, and when you're done counting the colors and measuring their widths and heights, I mean, okay, we're done, we understand. But then, if you try to increase the resolution, then something more happens, and then you have a better image, a better idea of what is going on behind it. And then if you increase the resolution again, a picture starts to appear. Do you know what this is? Yes. Yes, well done. Yes. So when we have full resolution and we can see everything, then this is the picture that was hiding behind those squares. And this is basically what happened with the globular clusters. So the data that we had before were not that accurate, were not that detailed. So the picture that we had was easy to describe because there was no complexity in it, there was no richness. But now we have a picture that looks more like this, and we could spend hours talking about this figure and about all the paint strokes and all the different colors that have been used to paint it. And this is basically what happened with globular clusters as well. And this happened in part thanks to the Hubble Space Telescope, which allowed us to take very, very deep and very, very precise pictures of the globular clusters. So in this case, you see a globular cluster, which is M80, is one of the most famous in the galaxy. It has been also widely studied. And you see that in the center, there is like a traffic jam of stars with a lot of stars piled up on each other. And then you see the extent of the cluster. So this image is very wide, so it goes outside. It's a combination of images, of course, because the Hubble Space Telescope has a smaller field of view than the extent of this cluster. But then you can still see, you know, a lot of stars, very detailed, and with more information that you can get. So there are colors, there are stars of different brightness. And then, because the Hubble Space Telescope is so detailed and with such a high resolution, it could even take images of the center of clusters. So this is an image of the center of Omega Centauri, the cluster that I showed you before. Before we saw it as a dot on a map. But if you look at it with the right instrument, then you see that it has a variety of things that are going on in its center. So you see stars of different colors, and you see many stars. Like if you see between the brighter stars, there is always something fainter going on there. And of course, these are not even all the stars that are there, because there are fainter stars that couldn't be imaged by HST. There could be something else entirely that is hidden there. And so this is one of the revolutions that helped us so much in increasing the complexity with which we describe globular clusters, because we have images that are complex themselves, so it takes time to process all the information that they contain. Another revolution happened thanks to Gaia. So Gaia is a satellite of the European Space Agency, and basically it is looking at the sky, and it looks at the entire sky, measuring positions of the stars on the plane of the sky, proper motions, so how the stars move on the plane of the sky, parallaxes, so distances that can be used to get the distance, and so on and so forth. A huge amount of data and of variety of data. This is useful for globular clusters because, for example, this is the extent of a globular cluster. You see a lot of dots over here. So if you look only at the position of the sky where this globular cluster is, you would get a lot of stars that belong to the cluster and stars that do not belong to the clusters. And if you look at how they are moving, so if you use the information that you have with the proper motions, you can select the stars that do belong to the cluster, so the red ones over here, and the stars that are just part of the galaxy behind. So they are not part of the cluster, they just happen to be behind or in front, in the same area of the sky where this cluster is. And this is huge. It's really important because then we can select only the stars that belong to the cluster and study those all together without having interlopers that could falsify our analysis or complicate the things a little bit. Good. So now we have a picture. We have our picture of a globular cluster. Yes. Yes, sorry. So this is milliarc seconds. Yes, so 1/1000th of an arc second. Yes, yeah, they are moving slowly. Yes, yes. Good. So we have our picture, we have our data, we have the brightness of the stars, the velocities. What do we do with that? If we just look at the data like this, it's really hard to understand what is going on because there is it's a lot of a huge amount of data of different types, and so it's really hard to put everything together. One way to do that is to use dynamical models. So dynamical models are models that explain how the things move depending on the galaxy, on the potential of the cluster, depending on what is going on in the cluster. And they can describe a system with different properties, and we will see in a bit what that means and what type of description a dynamical model can tell us. The important thing is that because the data are so complicated, we cannot describe them with simple models, because otherwise we end up describing the Sternnacht by using squares and saying, oh yes, there was some blue somewhere, which clearly it's not, doing any justice to the painting. So we need to have, an appropriate language, an appropriate description of what we see, also for globular clusters and their data. So that's one way to do it. So with dynamical models, which is what I do, is try to explain, to put everything together, to try and paint a picture that is more complex than what it was before. So, for example, one thing that dynamical models have taught us is how heavy stars and light stars behave in a cluster. So, as I said before, there are stars with different masses, and the most massive ones are the ones that evolve first, so they evolve more quickly than the light ones, but they are still part of the cluster. So you have stars that are heavy and stars that are a bit more light. And because the centers of the clusters are so dense, so stars are so close to each other, it happens very often that they pass by each other. So it's not like they clash into one another, but they pass very, very close. And that means that they perturb each other's orbits. And when heavy stars and light stars encounter each other, they change their dynamics. They change the way in which they move. And the final solution, the final result of this type of interaction is that all the heavy stars sink in the center and the other stars are outside. Why is this? What does it mean? So we see that the heavy stars are in the center and the lighter stars are outside, but why? This is because when they encounter each other, the heavy stars lose a little bit of their energy and they give it to the lighter stars. So if they lose their energy, they can only move a little bit around, but they cannot go very far. On the contrary, the light stars that get the energy from the heavy stars can move far, far, far away, and they can cover a larger extent of the cluster. So they go out to the periphery and then they come back. And that's why we see them everywhere around in the cluster, while the other stars stay in the center, because the heavy stars stay in the center because they cannot move more than that. So their energy is not enough to go very, very far. So this is a process that is called mass segregation, and it means that basically the stars separate. So the heavy stars end up in a system in the center, and the other ones are all over the place around. One consequence of this is that it can help us in doing some interesting discoveries. So now you will see a movie with two clusters side by side, and we will zoom in the center of the two clusters, and then the clusters do not evolve, but the simulation is looking at them, like rotating them to see them on all the sides and see what is going on inside them. So, yes, so here we are zooming in the clusters. You see that they already appear very different. The one on the left has many more stars, it seems, in the center. The one on the right has less stars. But we know, from a dynamical point of view, by looking at how these stars move, that these clusters have are both in the stage in which mass segregation happened. So, what is going on? Why are these stars so spread out? Do you have any idea? What can be that constitutes the heavy part of the stellar population over there that is in the center, that we cannot see, and that creates a similar situation as this one, where we can see the heavy stuff? What is heavy and invisible? Yes, black holes. Yes, indeed. So in the cluster on the right, there are a lot of black holes. And black holes, of course, we cannot see them, but we can infer their presence by looking at how the stars move. So we see that the light stars move in a way that suggests that there's something heavy over there that is occupying the center of the cluster, because they move as if, they have undergone this mass segregation. But if we don't see what is there, then it means that it's black holes. Okay. So black holes, they are also very important because, and understanding how many black holes and of what type of mass are there in a cluster can tell us a lot about the initial population of stars that created that cluster. And it can tell us a lot about also the dynamics of the cluster, because during the evolution, the black holes end up being very close together in the center. So if we were to simulate this cluster and to see what happens next, we would see that all the black holes would stay in the center, hang out with each other, sometimes form binaries, and at some point, for one reason or another, they would be all kicked out of the cluster. But this happens at a certain point, so it doesn't happen at the very beginning of the evolution. So if we see a cluster with still some black holes, it means that it's not at the end of the evolution, but there is still something going on. On the other side, if we see that there are no black holes, then we know that the dynamical state of that cluster is a little bit different. And it has, undergone several other dynamics effects. Okay. So another thing, as I said before, so with Gaia, we are very happy because by looking at the motions of stars, we can separate the stars that do belong to the cluster and the stars that are just in the foreground or in the background and are just part of the Milky Way and happen to be on top of the cluster or close to the cluster in the piece of the sky that we are looking at. So in this case, all the dots that you see over here are Gaia data. So each dot is a star, and it has been taken from it's one of the stars that have been observed by Gaia. So the gray stars are stars that are part of the galaxy, and the red stars are stars that are part of the cluster. And they have been selected based on how they move, like we did before, in the plot before. Why am I showing this again? Because before Gaia data, we thought that this black line over here was the edge of the cluster. We thought that there was nothing belonging to the cluster outside that thing. And all our models were built to try and explain this truncation, so this edge, this interaction with the galaxy, in such a way that this was the edge, and nothing was out of this. Now we see that there are plenty of stars outside. Of course, the density is very low, so the stars that do belong to the cluster and that are outside that edge, let's say, they are very few and they are very spread out. That's true, but still, they exist and they are a lot. And we have to take them into account to try and explain what is going on. So in part, this is due to the fact that the models that we were using before were just too simple. So they were not made to describe the complexity of the dynamics and of the properties of the stars that we can see now with the new observations. So these models needed to be updated so that this boundary can be pushed outside and then we can enclose more stars within the cluster. But that's not the entire part of the story, because still the stars do interact with the galaxy, because the clusters do not live in isolation. As we said before, they are part of the galaxy. And this means that when a star has enough energy to go outside in a certain position, it can get to the point where the potential attraction, the gravitational attraction of the galaxy is stronger than that of the cluster. And then it escapes. So it goes away. And this is how cluster eventually die out, because all the stars will escape at some point, and then the entire cluster disrupts. This is something that can be seen with another simulation. So over here, the red dots that you see in the back are part of a galaxy, and the green dots are part of globular clusters. So let me just begin so we can see how this is set up. So you see the central part is the galaxy, so it's just a simulation that shows what happens when globular clusters orbit around the galaxy. So you have the galaxy, which is the red area in the center, and all these dots are 10 globular clusters that are orbiting around the galaxy. And each one of these globular clusters has a lot of stars. So then we will see what happens when this evolves and when time passes. So while the globular clusters go around the galaxy, they experience different types of tidal effects. So the gravitational attraction of the galaxy changes. So if you go close to the center, the gravitational force from the galaxy is much stronger than outside. So it means that the gravitational pull on the cluster changes from the point of view of the galaxy, because its potential changes from the center to the out parts. And this means that stars can fall into the potential of the galaxy and can escape the cluster. And they create these stripes over here. And you can see that they are basically following the globular cluster orbit. And so the globular cluster is over here in this case. So there is a tail of stars that is going in one side and a tail of the stars that is going on the other side. This means that basically part of the stars are escaping as a queue behind the globular cluster along its orbit, and part of the stars escape in the front, so they go faster than the cluster and they escape in the front. This is basically the same idea as when you have tides with the sea and the moon. So you have enlargement of the sea on both sides of the Earth, even if the moon is only on one side. This is exactly the same idea. So you have stars that escape on both sides. And well, it started again. So if we keep it going and we arrive at the end, you will see that many stars get lost from these clusters. And it can happen that during various revolutions around the galaxy, at some point, it's not so easy to say which star belonged to which cluster. So it becomes a bit more complicated to trace each star back to the cluster that it originated from. Thanks to Gaia, we can see this in our Milky Way. So there is this group in Strasbourg. They have published a few papers where they use basically a software that looks at all the data from Gaia. The software is called Stream Finder because they are looking for streams. And with this software, they basically identify streams of data or overdensities, structures that are overdensities in the plane of the sky, based on the position of the stars, based on the motion of the stars, and on the distance. So they can trace streams that basically follow the orbits of some clusters. So for example, this M92 over here, that's a globular cluster, and it has its own stream over there. Palomar 5 is another one that is very famous. It's one of the largest and longest and thinnest stream. It was already known before Gaia, and it has been the focus of many follow-up observations to see what is going on. But now that you see that there are many more. This is another globular cluster, NGC 3201. But there are many streams, you will see that have names, and they are not related to a name of globular cluster like NGC something or omega sen. And this is because in some cases you see the stream, but you don't see the cluster. So it can be that the cluster is gone completely. So those are the last stars that remain from a cluster that has been disrupted completely around the galaxy. Or it could be that the cluster is on the other side of the galaxy, and this is just a part of the stream that was left behind. So to try and reconnect that with each of the progenitors is a very arduous task. In some cases it can be done, in some other cases it's much more complicated. Yes? So yes, that's a very good question. So because the stars move so slowly on the plane of the sky, how many years did it take? So Gaia was launched in 2013. And now this year there was the third data release. The first one was 2016. And so in the first one, there were already some proper motions measured. So in the first 2 or 3 years, let's say, 2 years, because it takes time to take the data, process them, and then release them. And there was a commissioning phase at the beginning. So let's say a couple of years. Of course, this means that the very first proper motions that were published were only for the very bright stars, the ones that are moving faster, that for which the proper motions could be measured with a certain precision and a certain accuracy. Now there are many, many more. So it's in the latest version of the catalog, there are 1.4 billion stars for which position, distances, and velocities on the plane of the sky have been measured. So it's a huge amount of data for the entire galaxy. Some of these stars do belong to globular clusters, so that's also great for globular cluster science. And yeah, so the more you observe, the better you constrain the observation, of course, the measurement of the proper motions, of course. But then it depends also on how close the star is, because if it's close, then the motion is larger, and this type of things. But yeah, it's a very good question. Yes, and so with the Hubble Space Telescope, also it is possible to measure proper motions, but the Hubble Space Telescope is a little bit different in measuring proper motions than Gaia. So Gaia is looking at the entire sky, and then it has a frame of reference inside the satellite in a way. So it always knows where it is looking at in the sky and in which direction, with which angle. With the Hubble Space Telescope, this is more difficult because you can always point at the sky in a different way. And because you are looking at a piece of the sky that is very small, it's very hard to know how it was oriented. So if you want to measure proper motions, you really need to know that, because otherwise you skew your measurements. And so in many cases, this can be done, because you can always find one star that you recognize in 2 images, and then you align your images on that one, and then you measure the proper motions of all the other stars. But this is a differential measurement of proper motions. It means that, for example, you will never know if the cluster is rotating on the plane of the sky, because you are measuring the displacement with respect to a given point. The only cluster for which it was possible to measure the rotation was 47 Tucanae, because it was so close to the small Magellanic Cloud. So the stars of the Magellanic Cloud were used as anchors to fix the images, and so it was stars that were not belonging to the cluster, and so in that case it was possible to measure the internal rotation of stars with proper motions, even before Gaia. But for all the other clusters, there was no way before Gaia to measure this type of information. And in this case, we are looking at a cluster. This is M5, is another very massive cluster in the galaxy. And for this cluster, so I put the figure, is image on the left, and on the right there are dots, of course, blue and red dots. And the red dots indicate stars for which a velocity along the line of sight has been measured, and these stars happen to move away from us. And the blue dots are stars for which the velocity along the line of sight has been measured, and those stars are coming towards us. What is happening to this cluster? If the red stars are going away and the blue stars are coming towards us, yes, it's rotating. Exactly. So this cluster is rotating. It's just like a ballerina, let's say, but tilted, because the angle of rotation is like this. So it's rotating like this on the plane of the sky. So you have some stars in half of the cluster. Most of the stars that are blue are on the right-hand side of the cluster in this framework, and they are coming towards us. Most of the stars that are red are on the other side, and they are going away. It's not exactly all the blue stars on one side and all the red stars on the other side, because on top of rotating, the stars are also moving chaotically around. And so some of the stars happen to be on the wrong side of the cluster at some point. But this rotation is really important, and it's really cool that we could measure it with line of sight velocities, so with velocities of stars in our direction, so not on the plane of the sky, but how they are moving with respect to us. And a nice thing is that this rotation can be connected with the shape of the cluster. So rotation can cause a cluster to flatten, so to be squeezed in the direction of the rotation axis. So in this image over here, we took the density of the cluster and we sliced it to get contours of the same density. So each set of points and lines of different colors indicate a different level, a different contour in the density of the cluster. And if you look at it, I don't know if that looks nice from the projector, but you can see that it seems like it's squeezed like this. So there is a long axis in this direction and then a smaller axis in this direction. And it seems that the direction of the minor axis is close to the direction of the rotation axis over there. So it could be that the cluster rotates and it flattens with respect to the direction of the rotation of the rotation axis, and so it becomes flattened due to the rotation. So this is one of the possibilities for which the shape of a cluster can change. So it can be modified by its own internal dynamics. And so it could be that it gets flattened because of this, or because of how the stars move with respect to each other. So with respect to anisotropy in the velocities. Or the other possibility is the effect of the external tides that squeeze the cluster in the direction of the stronger potential field outside the cluster. Good. Another puzzling thing about globular clusters. So everything that I have said so far are things that can be explained by looking at dynamical models and by using sophisticated dynamical models to try and interpret what we observe. And in some cases, numerical simulation come to the rescue when we want to see the details of the interaction between the stars and to really follow, for example, a star that evolves, that changes its masses and its brightness in time, and that interacts with other stars, maybe making binary systems and then disrupting them, and these kind of things. One thing for which all the models so far are still failing is this one. So this cluster is NGC 2808. It's one of the, again, famous clusters in the Milky Way. They're probably all famous to me, sorry. And this cluster is peculiar because you remember this plot from before, right? When we said that all the stars that are born from the same molecular cloud, let's say, they all have the same properties, they all end up following the same isochron. Well, when looking at this cluster and taking all the stars from this cluster to put them on this plot, what we see is something like this. So we see multiple sequences. So it seems like there is not just one population there, but there are many. So it's multiple stellar populations. And each population also has a different chemical properties. So they have different abundances for some of the elements that have been measured in terms of chemical abundances, and they are really a puzzle. The thing is that the puzzle is because you think you have a population of cats, for example, and then you discover that some of them are actually tigers. They look alike, especially if they are cubs, so they are small. They kind of look alike, but they are different. And why they are there, this is still something that we have no clue. So all the models that have been proposed, all the possible explanation to describe how tigers could be there, how tigers could end up there. So this population with completely different chemistry, with completely different photometric properties. There have been several explanations, but none has been successful so far. So people are still trying to come up with new ideas, to try and put dynamics into it, to see if that can change. And we are lucky because somebody is on it, also in this department. So I am super lucky, and I have the privilege of working with Laurent. And she's a PhD student in this department. She's sitting over there. And, she's working on this, trying to constrain the properties of the enrichment that is needed to create the elements that are so weird with respect to what we expect for globular clusters. So, to go back, are they really simple? Have I convinced you that it's not so simple? So yes, these clusters have many, many more things that they can teach us because they are complex. And when things are complex, everybody's happy because there is a lot to study, a lot of things that we can ask, that we can check, that we can see if we understand. And ultimately, trying to understand very well what is going on within these systems and trying to characterize their populations, trying to understand how the weird ones end up being there, how stars are moving, how they are interacting with their galaxy, can help us answer these questions. So knowing how a cluster is right now could help us in understanding how it was at the beginning, because not all shapes of clusters at the beginning end up during evolution to something that we see today. So we really need to get the right initial conditions, let's say, to get a system that evolves to what we see today. And on the other side, globular clusters live in galaxies, and how they interact with the host galaxy and how they interact with the other stars can tell us a lot about how the entire galaxy formed and how the stars in the galaxy ended up where they are, like we saw before with the streams. So this is to say that this is not the end of the story, and it's just the beginning, actually, because we are living in an era of exciting new data that are super awesome and provide very many questions, which is great. When data provide questions and not answers, that's when astronomers get happy. And then it means that we really need to push our models to try and interpret those data so that we can understand what is going on there. So stay tuned, because surely there will be something amazing coming out of these systems soon. And thank you.
Thank you very much, Alice, for this great talk. I enjoyed it a lot myself.
Thanks.
So now, if there are any questions, please ask them. And in the meanwhile, you can also start filling up the survey. Yeah, so...
It sounded like you were saying about the past that there were formed many clusters. But what about today or in the future? Will they also form clusters? Because it sounded like they will fall apart and integrate in the Milky Way or some other galaxies. And there will be no more clusters in the future, probably. And the other question is, what is the number where you can say it's a cluster of stars, and where is this border? Yeah.
These are very, very nice and interesting and important questions. So yes, the clusters that we see today, the old ones, will end up being disrupted, so they will at some point no longer exist. But galaxies are still full of gas, and they are still full of molecular clouds. And from those, they can keep clusters keep form. So there are some areas, especially in the Large and Small Magellanic Cloud, which are close by, but also in other galaxies, where we see star formation in action. And we see that there are stars that are forming in clusters over there. So maybe not as massive as the globular clusters that we see today, but still there is something going on. So clusters are still being formed today, and probably they will still until there is gas from which they can form. And then the other question, sorry. The number, yes. So it's so this is another thing that is very hard for astronomers, defining things. So you all know about Pluto, right? So for clusters and other stellar systems is very similar. So it's really hard to put an edge to a definition. But in general, star clusters are systems that go up to 10 to the, so 1 million solar masses, more or less, in mass. And they overlap partially with a class of systems that is the dwarf spheroidals, so galaxies that are very small and that also orbit around the Milky Way. The main difference is that they have dark matter and globular clusters do not. So that's the way to tell them apart. But in some cases, there are some overlaps in certain parameter spaces. Yes.
Any other questions? Yeah.
How many global clusters have been studied to a level where you can see, okay, it's only cats, or is the cat tiger the only one?
That's an excellent question. And you know that before I said that astronomers were really happy back in the days when they could get like the cleanest sequence in their color magnitude diagram. Now the race has become find the one with more sequences. The simple things are not, you're not a good astronomer if you find something that is simple. No, I'm oversimplifying. But so actually this is a problem that has been, it's really a mystery for the community. So what has been done is that, so the first time that that this weird, tiger population was observed, the people were puzzled. And then they started trying to observe many more clusters to see if this was just a case or if this is really widespread. And they kept finding tigers everywhere. And then they started thinking, okay, maybe it's the Milky Way. Maybe we need to move somewhere else and observe some other clusters, and maybe those will not have these weird populations. And then they looked at clusters in the Magellanic Clouds, which are close by, so we can really identify stars, or in the Fornax galaxy, the one that I showed before, which also has stars that can be resolved. And multiple populations appear everywhere. So there are tigers everywhere. So then people started looking at younger clusters. And it seems like clusters that are younger than 2 billion years, do not show signs of these weird populations. But it's not many clusters of that type around us, so it's really hard to really put a limit to this. But yes, people are like observing everything that looks like a cluster to see if there is any tiger in there, to see and try to quantify a little bit more this phenomenon. Yeah.
How do you know there's up to no dark matter in globular clusters?
That's a good question. A dynamic one. I love it. Okay, so yes. So when you look, when you see things in the sky, when you see galaxies and stellar systems like this, you can always measure the light that comes from those systems. And because masses, I mean, there are no giant scales that we can put there to measure the mass of these things. So we need to infer the masses in some other ways. So to measure masses, usually you use the movement of stars. So by looking at the dynamics and how they move, we know how much mass is there. And then if we compare the mass with the luminosity, we see that the value that we find, the mass luminosity ratio is called, as a number that is low enough to be consistent with just stars. Because if this number becomes very high, it means that there is way more mass than luminosity, and this mass needs to come from somewhere, and it comes from somewhere that doesn't emit light. So that's how dark matter is typically identified. But if you see that the number that you get is reasonable for stars, then it means that there is no need to account for dark matter over there.
Any further questions?
Okay, sorry, this is, if it's a naive question, but what is the time scale of this? So these streams that you showed.
Yeah.
So let's say to go from a really spherical cow to one of these streams, what is the time scale and how is this compared to the lifetime of a star?
Yes, that's a very good question. The answer is that it depends. Sorry. No, it depends on the type of stars, on the type of system that they are in. So there are some globular clusters that are very, very tightly bound. So the stars are so packed together that before they have to expand to a certain level, and then they can start losing stars. Because if they are too compact, then they cannot feel what is called the Roche lobe, which is like the mathematical formulation to explain this interaction between the tides from the galaxy and the dynamics of the cluster. So whenever they feel this thing, then they can start losing stars. So if this cluster is too compact at the beginning, it can take a lot of time. It can take billions of years. In other cases, the cluster is born already feeling that thing, and then it can start losing stars immediately. So it really depends on how these things form. And before you ask, we still don't know how these things form. So this is one of the other things that we are still trying to put together and to understand, to also define and understand how these two things can happen at the same time. Why there can be stars that are closely packed together and stars that are more widely spread, and that both, ages or immediately streams appear. Yep.
My question is, why are these globular clusters so spherical and not ellipsoids like galaxies? Where does the angular momentum go?
Say that again, sorry.
Why are globular clusters so spherical and not ellipsoids like galaxies?
Okay, the difference is that globular clusters do not rotate that much. So so typically they rotate very slowly with respect to how fast and how different are the motions inside. Like the chaotic motion, the random motion of the stars is way higher than the ordered motion, as we call it, so the rotation of the cluster. So that's why the flattening is mild. So the simple approximation of considering them as spherical, it's wrong, but it's not that wrong. So it's still, the flattening is still quite small. And one of the, in part, this is puzzling because even if the rotation is not that strong, still there are tides, still there are many other things that could contribute in flattening them a little bit. So yeah, this is still something that is going on, but but the main difference with respect to ellipticals is that yes, they have a different, probably also formation scenario, and so yeah, the things that make ellipticals ellipse maybe do not work in cluster in the same way.
Any other questions? I have one myself. Sorry.
Thanks. My question would be, why do these clusters form at all? I mean, they could be flying around in some unstructured way, but why do they form? Do they form around, I don't know, a black hole in the middle, or do we know?
So it seems like first the clusters are formed, and then maybe a black hole could form in the center at a later time. It's still not clear if there is at all a black hole in the center. It seems like there isn't. So the observations that have been done do not seem to suggest that there is anything over there. But so stars form like this because you need to imagine like a cloud, so a cloud of gas. And then this cloud at some point starts collapsing, and it collapses, and because there are overdensities here and there, so the cloud is not homogeneous with all the same density everywhere, where there are clumps, the collapse happens a little bit faster, and then you form stars. But because the entire thing was a cloud that was connected before, then these stars remain connected to each other, and that's how they form clusters. So the idea is that one. And yeah, now we think that stars form mostly in filaments, and then, but then still, these filaments are connected, and so then you can still come up with clusters after that. Yes. Yeah. Yes.
Is there a limit in size for the global clusters? Or can a global cluster form a galaxy?
Oh, that's a good question. So I think that globular clusters are too few to account for the mass of the galaxy, but because we don't really know how galaxies formed, this is something that is still being investigated. We don't have a clear idea of how globular clusters or galaxies or anything formed. We still, we have an idea of like a hierarchical formation where you form small pieces and then they merge together and they form something bigger. But how the small pieces formed, who knows? So it's still, it's a matter of saying whether it was born first the egg or the chicken. If you decided it's the chicken, then the egg, you know how the egg forms, but you don't know where the chicken comes from. So that's the idea. And so, yes, in principle, yes, they can contribute in, this merger and this hierarchical accretion that creates, bigger structures. But probably you cannot build a galaxy only with globular clusters. You need something more because they are not enough.
And about the black hole, so my question. So you said that it's more likely that the black holes that form within the global cluster fly away.
Yes.
Than merging.
They also merge, yes. So yeah, thank you. That's an excellent question. So actually now that gravitational waves have been observed, this has been a hugely debated topic and very nice to follow up with dynamics. So yes, basically during the evolution you have all the black holes that sink in the center because they are heavier, and when they are there, they can create binaries, and they can interact with other black holes and with other stars. Then to each binary, a set of things can happen. So it can happen that a binary gets tighter and tighter, and then the two black holes merge. And some of the merging events measured by LIGO, for example, have the mass range that makes sense for black holes that could be in globular clusters. So that could be like the place where these things happened. In other cases, the binaries can be disrupted. So it can be that you have a binary with two things that orbit each other, a star and a black hole, or two black holes or two stars. Something else arrives, and it either breaks up the binary, or the third thing that arrives takes the place of one of the two things and kicks out the other one, or a certain set of outcomes can come out of this. But in the end, due to this type of dynamics, either the black holes merge and then you have a bigger black hole that creates another binary and so on, but eventually they all get kicked out. Yes.
Good, so if there are no more questions, I would like to thank Alice again for this great talk.
No, thank you for being here.